In the last video, you were introduced to the idea of natural deduction. In this video, we're going to introduce some of the basic rules that natural deduction uses, the ones with which we reason step by step from our premises to our conclusion. So the goals of these proofs will be to apply the rules that we need, the ones that allow us to prove the conclusion on the assumption that the premises are true. In this lesson, we're going to learn to use 7 of the most basic proof rules in the natural deduction system, and that will include learning how to apply the schematics for these rules to particular lines of a proof. And we're also going to introduce this basic distinction between 2 kinds of rules, introduction and elimination rules. But we'll start with a very simple rule to give you a feel for how the rules of a proof in this system work. So our first rule is reiteration. What does the rule do? It tells us that we may repeat a line of a proof on a new line. So we have on the left-hand side here a schematic. The schematic shows the basic structure for the rule. Remember that our proofs have numbered lines, and those lines are designed to move us from the assumption of the premises to show the truth of the conclusion. So when we use the rule, reiteration, M and N will be substituted with actual line numbers of the proof. That curly A should be somewhat familiar. It's one of our metalinguistic variables. And like any metalinguistic variable that we've used, it's one that can be substituted with any sentence of truth functional logic. If you want to review metalinguistic variables, go back to video 2.5. Not only do we see the lines M and N and the sentence that we're repeating, curly A, whatever we substitute for that, there's also a justification, R, M. R is the abbreviation for reiteration, and M is the line number of the line that we're repeating at line N. So let's look at an example of this in the structure of an actual proof. Let's say the sentence, "It's not the case that A or not B," appears on line 5. The reiteration rule allows us to repeat that sentence of truth functional logic on any later line of the proof. So in this example, the sentence is repeated at line 17. And then to the right of the sentence, on line 17, we see the justification for writing that line. So we appeal to the reiteration rule, abbreviated R, and the number of the line we applied the reiteration rule to, line 5. You'll see this basic structure, numbered lines, metalinguistic variables that characterize the rule, and the structure of the needed justification. That will be the case for all the rules we're going to look at in this video. Now, reiteration can apply to any sentence, no matter what logical connective it involves. But the majority of our rules, including the rest of the rules we look at today, apply to sentences based on their main connective. So by the end of this lesson series, we'll have introduced 2 types of rules for each connective type: negation, conjunction, disjunction, conditional, and biconditional. The one type of rule will be the introduction rules. These are rules that state conditions for adding a sentence that contains one of our logical connectives, and we'll add it to a new line of the proof. So we're going to have a rule, conjunction introduction. That's a rule that allows us to add a sentence with conjunction as the main connective on a new line of the proof. Elimination rules, on the other hand, are ones that apply to sentences containing one of our logical connectives, and they give us conditions for eliminating that connective in a sentence on a new line of the proof. So we have one of our rules is biconditional elimination. We apply biconditional elimination to a line of the proof with a biconditional as the main connective. And that, along with other conditions, allows us to add a new line without a biconditional as the main connective. The idea behind these two types of rules is this. Let's say we start with premises that contain biconditional and negation. And let's say also that our conclusion contains a conjunction. What we need is rules that allow us to form sentences from the original biconditional negation sentences by eliminating the original symbols, since they don't appear in the conclusion. And then we have to introduce a symbol, conjunction, that wasn't in our initial assumptions, but was in our conclusion. So the rules allow us to do so, and there just will be some conditions for applying these rules. In the rest of this video, we're going to cover the most straightforward introduction and elimination rules. And we'll start with the rules for conjunction. Conjunction introduction is our first rule, and this rule allows us to, on a new line, add the conjunction of any two sentences that appeared on separate lines earlier in the proof. So again, the schematic shows the basic structure of this rule. It can be applied to any proof that shows sentences with this basic structure somewhere in the proof. So the schematic here says when we have some sentence A on line M and some sentence of truth functional logic B on line N, we can add the conjunction of A and B on a later line. And then we justify the new line by the rule conjunction introduction, here abbreviated with our symbol for conjunction and I. And then we also add the lines M and N on which we found our two conjuncts. And to the right here we have our example. So we're going to see parts of the proof where the sentence S appears on line 4, the sentence R or T appears on line 7. The conjunction introduction rule allows us to add S and R or T as a new sentence on some line of the proof, here line 11. So the introduction of a new sentence containing conjunction is justified by the conjunction introduction rule and the lines 4 and 7 where the conjuncts initially appeared. And note that one of our conjuncts is a complex sentence because the metalinguistic variables in the schematic don't just have to stand for atomic sentences, they can stand for sentences of any degree of complexity with any number of connectives. The idea behind conjunction introduction is simple. If we can show that two sentences both follow from our previous assumptions, it seems pretty reasonable to acknowledge that the conjunction of those two sentences will also follow from our previous assumptions. For each of these rules, I'll try to motivate it somewhat, because the idea, again, behind natural deduction is that it relies on some more intuitive and straightforward reasoning rules that lead us from the premises to the conclusion. Again, as we'll see with every connective, there will be both an introduction and elimination rule. So we just saw the introduction rule for conjunction, and now we're going to look at the elimination rule for conjunction. That rule tells us that if a conjunction appears on a line of a proof, we may add on a new line either of the conjuncts. So for conjunction elimination, we actually have two simple schematics. The first shows that if we have a sentence A or B on line M, we can add the sentence A, one of the conjuncts, as a separate sentence on a new line. And we can justify that rule with conjunction elimination, the abbreviation &E, and the line number m on which the conjunction appeared. But there's also this second schematic. If we have that conjunction, we can also add the other conjunct on a new line. And that has the same justification. So this rule allows us to add either conjunct, and we can allow, and as we'll see in a second, we can add both conjuncts on separate lines. So let's look at this example. We see the parts of the proof where the sentence not S and if R then T appears on line 6. The conjunction elimination rule allows us on later lines to add the conjunction not S as a new sentence on some line of the proof. And so not S was added on line 8. We can also use the same rule to add the other conjunct if R then T on another line, here line 9. In both cases, the introduction of the conjuncts as new lines is justified by the conjunction elimination rule and the line 6 where the conjunction initially appeared. Again, let's consider the motivation for this rule. It's pretty simple. If we can infer a conjunction from our initial assumptions, we should also be able to infer each of its conjuncts separately, since the conjuncts will be true whenever the conjunction is.